It takes only about 3,140 liters of water to fill it. Yet no amount of paint can cover its entire surface. This seemingly impossible object kept European mathematicians arguing for more than 30 years, before calculus was even born. In 1641, Evangelista Torricelli created a strange solid on paper in Italy. He was Galileo's last student, and 2 years later he built the world's first barometer. The solid he created stretched endlessly to the right, yet its total volume was trapped below a finite number. The senior mathematician Cavalieri marveled that Torricelli had extracted a finite magnitude from infinite depth. By contrast, the French mathematician Roberval objected that it was false and impossible. The news spread across Europe through Friar Marin Mersenn's network of letters, and the dispute continued for more than 30 years. In 1671, when Wallis presented this solid as evidence, Hobbes scoffed that one would have to be mad to understand it. Newton was born the year after this discovery, and Leibniz had not even been born yet. Torricelli calculated the volume using the era's newest technique, the method of indivisibles, and also supplied a separate proof in the ancient Greek style. No record tells us who coined the name or when. Later generations compared it to the archangel's horn that sounds on Judgment Day, and called it Gabriel's horn. Now we will build the horn, fill it with water, and see why painting it is the one task we can never finish. We need only one curve. As x grows, the curve falls. Y equals 1 divided by x. The rule is simple. For x greater than or equal to 1, if the horizontal coordinate is x, the height is 1 divided by x. At x equals 1, the height is 1. At x equals 2, it is 1 divided by 2, and at x equals 10, it is 1 divided by 10. No matter how large x becomes, 1 divided by x is never exactly 0. The curve approaches the floor forever without touching it. Rotate the filled region under the curve once around the x-axis, like clay on a potter's wheel, and a solid appears. On the left is the profile formed by the curve and its reflection. On the right is the actual horn produced by revolving it. Let one coordinate unit represent 1 meter. Then the opening also has a radius of 1 meter. With this scale, the radius of the cross-section at the dimensionless coordinate x is 1 divided by x in meters. Infinite length alone does not determine total size. We must also see how quickly each section narrows. Now let us open the endless horn's 2 ledgers and calculate how far the water and paint each go. First, how much water fits if we seal the opening and pour it in. Second, how much paint is needed to cover the surface. Because the object is infinitely long, we want to say both are infinite. Today's paradox takes aim at that intuition. With an opening radius of 1 meter, the two answers part ways. The volume is pi cubic meters, while the surface area grows without bound. Historically, Torricelli proved that the volume was finite. The infinite surface area was established later. Cut the horn from its opening at x equals 1 to the point x equals L, and the 2 ledgers can be summarized in a single line. First, the water. A thin slice of the horn can be treated as a very thin cylinder with radius 1 divided by x. The area of a circle is pi times the radius squared. So the water slice shrinks like pi divided by x squared. Adding all these slices from the opening at x equals 1 to the point x equals L gives the volume of the truncated horn. The calculation gives pi times the quantity 1 minus 1 divided by L. As L grows, 1 divided by L fades to 0, so the volume creeps upward toward pi from below. Pi cubic meters is about 3,140 liters. That is roughly 15 household bathtubs, or about 3.1 metric tons of water. Now for paint. Over a thin interval, the lateral surface is calculated like a band. Circumference times slant length. Including the square root factor that corrects for the horn's slope, gives the exact surface element. Substituting the radius and slope gives 1 divided by x, multiplied by the square root of the quantity 1 plus 1 divided by x to the 4th power. Therefore the surface area exceeds the simpler integral of 1 divided by x. That integral evaluates to the natural logarithm of L. The natural logarithm grows slowly, but it never stops. Slow and stopped are not the same. Eventually it goes to infinity. Plotting the actual values makes the difference visible. The water curve above hugs pi, while the paint curve below keeps rising. The initial interval, which includes the steep opening, has an area of about 15.18 square meters. After that, each 10-fold increase in the endpoint x adds close to 14.47 square meters. Why do the inside and outside of the same horn behave differently? The secret is how many times the radius is multiplied in each cross-section. For water, each cross-section is a base area. It determines how much water fits at that position. For paint, that same cross-section is a circumference. It determines the distance around the wall at that position. Suppose the radius shrinks to 10% of its original value. The circumference also becomes exactly 10% of its original value. But area contains two factors of the radius, so it shrinks to just 1% of its original value. A water slice shrinks faster because it contains an extra factor of the radius. A paint strip shrinks only in proportion to the radius. That difference separates a finite total from an infinite one. At position x, the water element behaves like 1 divided by x squared, while the paint element behaves like 1 divided by x. As more terms are added, the partial sums of the reciprocal square series approach the finite value of about 1.645. By contrast, the series with terms 1, 1 over 2, 1 over 3, and so on is the harmonic series. Each term approaches 0, but the partial sums grow without bound. Group 1 over 3 and 1 over 4, and the result is greater than 1 over 2. Group the next 4 terms, and the result is again greater than 1 over 2. We can form infinitely many groups whose sums exceed 1 divided by 2, so the partial sums grow without bound. They just do so very slowly. For a partial sum of the harmonic series to exceed 10, you must add all the way through the 12,367th term. This horn turns the difference between two series into a solid. Its volume converges to a finite value, while its surface area grows without bound like the harmonic series. Julian Flarin turned this intuition into a tiered cake made of cylinders whose radii shrink as 1, 1 over 2, 1 over 3, and so on. This cake has finite volume but infinite lateral surface area. You can eat it, but you can never finish icing it. Now we will increase the endpoint x tenfold at each step and watch how water and paint part ways. When the endpoint x corresponds to 10 meters, the water reaches 90% of its maximum. The surface area is about 15 square meters. When the endpoint x corresponds to 100 meters, the water reaches 99% of its maximum. The surface area is about 30 square meters. When the endpoint x corresponds to 1 kilometer, the water is already extremely close to pi. The surface area is about 44 square meters. When the endpoint x corresponds to 10 kilometers, the water gauge has nearly stopped, but the surface area grows to about 59 square meters. When the endpoint x corresponds to 100 kilometers, the water agrees with pi through 4 decimal places. The surface area is about 73 square meters. Even when the endpoint x corresponds to 1 billion kilometers, the water still hugs pi. But the surface area has passed 174 square meters and keeps growing. Now comes the sharpest objection. If filling the horn makes liquid touch the entire wall, has it not already been painted? If pi cubic meters fills the horn, water touches every part of the inner wall. Pouring in paint instead seems as though it should do the same. Then a finite amount of paint has covered an infinite area. That directly conflicts with the result we just calculated. This objection is only half right. Filling the horn does make the paint touch the entire inner wall. The problem is that the word paint hides two different meanings. Ordinary painting requires the paint film to have the same thickness everywhere. The amount needed is approximately surface area times thickness. By contrast, when the horn is filled, the layer of paint touching the wall grows thinner along with the horn as we go deeper. A paint film whose thickness approaches 0 fast enough can touch a wall of infinite area, while using a finite total amount. The intuition that infinite area requires infinite paint contained a hidden assumption. The thickness stays constant. Still, if real paint made you uneasy, that intuition was also right. This horn itself cannot be built in reality. If the paint film is 0.1 mm thick, then at 10 kilometers the horn's radius equals the film thickness. Even if we lower the threshold to a molecular scale of 1 nanometer, the radius becomes smaller than that, around 1 million kilometers. The orange point marks a film thickness of 0.1 millimeter. The red point marks a radius of 1 nanometer. A real particle's passage limit also depends on its diameter and shape. Gabriel's horn is not a fabrication blueprint. It is a thought experiment exposing cracks in our everyday intuition about infinity. Drop one dimension and we meet the Koch snowflake, a flat cousin with finite area but infinite perimeter. The coastline paradox, in which a coastline grows longer as the measuring stick gets shorter, belongs to the same family of infinities. Hilbert's hotel, which makes room for more guests even when full, and the St. Petersburg paradox, with infinite expected value but a fee that still gives us pause, are relatives too. As early as the 14th century, Nicole Oersma constructed a plane figure that was infinitely long but had finite area. May we calculate the volume of an infinitely long figure? May we add indivisible pieces? The debate struck at the foundations of mathematics. Not only Hobbes and Wallace but also Isaac Barrow and John Locke joined the dispute, shaking the boundary between mathematics and philosophy. After Newton and Leibniz developed calculus, the turmoil finally subsided only when the concept of limits was made rigorous in the 19th century. Hobbes never accepted it. He even suspected that Wallace was defaming a dead man, insisting Torricelli could not have proved such a result. The following year, Hobbes argued that the solid was not infinitely long but merely lacked a fixed endpoint. Torricelli himself remained calm, merely calling his solid paradoxical, so to speak. Finally, let us summarize this horn's conclusions in 3 lines. The horn has infinite length, and its volume converges to pi cubic meters. Its surface area never settles at any finite value. The key was simple. The volume formula contains the radius squared, making the total finite. The surface area formula contains only the radius, allowing the total to grow without bound. Filling and painting to a constant thickness are also different operations. A single hidden assumption created the paradox. No workshop in the real world can build an infinitely long horn. Yet on finite paper, we can prove that it can be filled with a finite amount of water, and still cannot be painted to a constant thickness. Calculation takes another step where intuition stops. That is the resounding message carried by this slender horn. If you enjoyed today's video, please subscribe, like, and turn on notifications. See you again in the next story.